Here to present our research paper on wireless power transfer for automated industry applications, a prototype. Our paper ID is 96. This paper is presented by
Vachil Singh,
Rajan Mandari,
and Yaduraj Singh. We are students of EEE Department, ACET, Amity University, Noida. These are the list of content that we will be covering in our presentation. We will start with an introduction. So what is wireless power transfer? The technology of transferring power without wires using electromagnetic induction as principle is known as wireless power transfer. In transmitting circuit, we will basically increase our frequency of the supply. Then we have our medium to supply to transfer power. Then in receiving circuit, we have our rectifier to make the frequency of desired frequency to fed to our load. So what are the problems that we face? First is faults in the cables. Second and third, to making system isolate for better sealing and waterproofing. Then we have then the friction we have in male and female part, the wear and tear. Then replacing backup battery with wireless power transfer, as batteries are basically dangerous. So the different types of wireless power transfer. First is near field. Second is far field. In near field, when the wavelength of power is less than half the distance of transmitting and receiving circuit, then it is near field transmission. When it is more than half, then it is far field transmission. We have inductive coupling and capacitive coupling in near field, in propagating magnetic, electromagnetic, microwave, and photoelectricity in far field. Now comparison between of available technologies. As we know, there are various technologies available, but for our project, the most desired one is magnetic resonance. It has many advantages. First is the multiple input and multiple output is possible. Efficiency is very high as compared to others, and the alignment of coil do not affect the efficiency of the system. But it has disadvantages also, like it is limited to few meters, but it is more than that of inductive coupling. Inductive coupling is only limited to few centimeters, so basically it is more than inductive coupling. So we will be using magnetic resonance. Now in our block diagram we have power supply, AC to DC SMPS basically. Then in transmitting circuit we have signal generator, power amplifier, and inverters. Then driver loop for our transmitting coil. Then we have our receiving coil attached with load loop. In load loop, basically we have rectifiers to make the frequency of desired range for our load. Then the next part will be explained by Vachil Singh.
So this is the loop representation of the earlier circuit described by Yadraj. In this, as we can see, we have RLC parameters. The RLL parameters are of the loops that were in the figure mentioned earlier. And the capacitance values, we have used ceramic capacitors so as to provide for the necessary capacitance in order to provide resonance. The drive loop and load loop are of 28 centimeter in diameter and they are of single turn. The TX coil and RX coil are of spiral in nature, having 6 turns with 1 centimeter pitch. They have an outer diameter of 59 centimeter, and all these loops are made up of 2.54 mm thick copper wire. These are the equations derived by using Kirchhoff's current law and Kirchhoff's voltage law from the earlier loops. And this is the relation between a mutual inductance and coupling coefficient using the inductance of various coils. So coming to the simulation part that we have done regarding the 3D orientation and variation of fields and resonance, we used MATLAB R2018B software for our simulations. We used two spiral model. Here we can see the TX and RS coils having 6 loops and how they are oriented in 3D with the variation in distance between them. In this simulation, we can see how the magnetic fields vary across the various loops. In this simulation, we are able to see what is the effect of resonance when the system comes at resonant frequency. Then the impedance increases, and at the same time, we can see that the S21 magnitude or the transfer parameter increases to its maximum. That is, the power transferred is maximum at resonance. So coming to the hardware part, this is the overall block diagram. in which we can see that there is a power supply to 20 volt which is available in our household. It is then fed to AC or DC SMPS to convert it to 24 volt DC power supply. And this is the power amplifier motor driver module, in which we have fed a 200 kilohertz signal generator from Arduino Uno by coding it in order to provide 200 kilohertz signal, and the DC power is fed via AC to DC SMPS. And then this power amplifier feeds the drive loop, which is of single turn, and it then feeds through the TX coil, which is of 6 turns, and there's a step up in between, and here the actual power transfer happens. And after it, the receiver coil is also of 6 turns and of the same dimension as of the TX coil, and after it is again rectified and fed to the load. This is the initial circuit which we implemented, and this is the modification of the earlier circuit. Here we can see the SMPS converting the power into DC, and then this DC power is fed to the motor driver module, and the high frequency 200 kilohertz signal is fed via this Arduino Uno, and this motor driver module then works as a transmitter circuit and feeds the 200 kilohertz power to the drive loop. This drive loop converts the step up operation, and then the power is transferred again step down and fed to the load. So the result portion will be explained by Mr. Rajan Bhandari.
Here is the output of our project, in which at 30 centimeter distance we are getting 22.3 volt peak to peak at primary side and 18.0 volt at secondary side. Whereas at 50 centimeter we are getting 24.0 volt at peak to peak at primary side, and at secondary side we are getting 18.6 volt at 50 centimeter. Then the observation table, it is at the 50 centimeter. We are in this table we are trying to calculate the power at across the 330 volt, and at primary side we are getting 0.68 watt power, and at secondary side we are getting 0.44 watt. Then when we calculate the efficiency, it will comes out 65%. Then the future scope and the application. Wireless power transfer market is grow $17.4 billion in 2020 because of large, great development and vast investment. The few various future proposed applications are wireless charging electric vehicle, in which the vehicle is not need to connect it with charger. It just start charging when it comes to electric wireless charging pads. Then there is a solar powered satellite, in which the large satellite having large solar panel is placed in space, which converts solar energy to electrical energy and transfer to earth by using microwave wirelessly. Then there are many applications like wireless power drone, wireless power home appliance, and universal power source in emergency. Then advantage of wireless power transfer is it is easy to make waterproof and less wear and tear in wireless power transfer, because it does not require any wire. Then it is industry friendly because it removes very excess of wire. Then it is environment friendly because it do not require any disposal of batteries. And it is aesthetic because it do not require any wire, so it make beautify the environment, and it also reduce the battery size. Then the limitation is because of the constraint and research, there is a limitation of efficiency and range, because with increase in range the efficiency get decreased. Then due to the very requirement of rectifier and high frequency generator, its initial cost is high. Then here is the reference for our project and paper. Thank you.
Thank you.
Thank you.